check, check. Check, check, check. There we go. All right, cool. So, 3.1 starts with exponential functions. I don't have a lot of slides for this. I think that you guys have seen exponential functions and exponential growth for a while already. So we're just going to be doing a quick refresher, touching base on some of those things, asking any questions that you might have. Okay. So here are the success criteria for today. I want to make sure that you can evaluate exponential functions, that you can graph them, evaluate functions with base e. Do you guys remember e? E is a number. Anybody remember what e is equal to?
2.7 something something.
2.71, blah, 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 blah. That's correct. So e is very much like, thank you. E is very much like pi. It represents a number. It does go on forever. You will use it a lot, especially when you're doing exponential growth and stuff. So get used to it. And then we'll talk about the compound interest formulas if we have time to get to that. We have that simple interest. We have the compounded, which you can do regularly and stuff. But then there's the continuous. I think you guys have seen those formulas before. If not, let's just real quickly. When you're doing the simple interest, you're usually talking about annual, right? So you have some account, you're putting money into it, it's getting some kind of amount of interest in a year, and then just that simple interest. But then there's that compounding. And what they mean when they do compounding, a lot of your credit cards do that. Anybody have credit cards? You got that debit card? If you have a credit card, they love to do compounding, but it actually has to do with charging you the interest piece. And what they'll do is every month, they'll see how much you owe, and then they'll put a certain percentage, Leah, on top of that, on top of what you owe, and that becomes part of your new debt. And then they keep doing that every month. If you left that alone for a while, Jesus Christ, you're paying that for a long time. Especially those people that like to pay the minimum balance on credit cards. You really want to be careful with that because that really starts to back up quickly. Okay. Thank you. Thank you. So exponential functions with base b are defined as f of x equals b to the x, or y equals b to the x. What do we have on the left side is our function notation. Over on the right side, we have our equation notation. That is a basic exponential function there. Now, b has to be greater than 0. If b is equal to 0, then you no longer have an exponential function. You're back at our scenario where you have just a constant, beep, that line kind of line, a y equals some constant. Before, when we were working with other functions, there were a couple things that we could do. Let's take, for example, a quadratic equation. We know that the basic quadratic is y equals x squared, yeah? But there was a couple things that we could have done to it. There's actually about 4 things that you can do to it. Can someone just name one of them? We can stretch it, so we can do a vertical stretch or compression. There was a variable that was in charge of that. What was it? I heard it somewhere. A. So we had A, correct? What else could our parabola do besides getting stretched compressed? We can move it left to right. Do you remember which variable did that? It was H, right? So we have a built-in H in there. And I just want to remind you that H is the value that shifts you left to right. And it's always kind of, you got to be careful because there's that built-in negative. So notice I didn't put the H in the red because it's really not negative H that controls where you're going. It's just H. There's another thing that you can do. You can move it up or down, which is our K, right? So we're going to go ahead and throw plus K up there.
That's an R.
K. It's a capital. It's a lowercase k in cursive.
It's K.
You want to get it, Evan? You probably can't even read cursive.
One more thing. There's one more thing. We have 3 of them. There's 4 things. Say that one more time. We can reflect over the x-axis. Do you remember how we take care of that thing? We could do a negative in front, right? Okay. Now technically, we could also reflect across the y. But can you really see it with a parabola? No, unless it was shifted. So I'm not even going to talk about that. I want to take what we've done here, and I want to make some connections. Remember, our mother function is y equals x squared, correct? That is the parent function of this. And then from that, we know that there's a bunch of different things that we can do. What you're looking up top, f of x is equal to b to the x, that is also a parent function. That's mommy function right there. And we can also change some things. What's up? Yeah, so, I thought you were like, no. Okay. So, I just saw someone go, it kind of does this, but doesn't it? Right? Okay. Here's what I want to do. Y equals b to the x. This function, this new one over there in the green, we can move it up or down. Do you guys remember what used to do it before? K. We're still going to use k here. And it's going to be sitting. That's horrible.
Connected.
Okay? So our k's out there. So that means we can take our exponential growth, we can move it up or down if we needed to. Could we move it left to right? Could we move it left to right?
Oh, isn't it in the exponent though? There's an h.
We could move it left to right. Do you remember which variable did it?
It's h.
It was h. And usually, almost all the time, we would see x minus h. That showed us that, right? Same idea. So here we're going to have x minus h. Still doing the same thing. It's going to shift it left to right. Okay, because we're changing x values here. And if we want to change how fast it's growing, which technically is a stretch compression, we're going to change a. And a will be up front as well. Okay? Say that one more time.
Wouldn't A and B be the same thing?
No. A and B would not be the same thing. Here's the way that I think about these, just so that you can think about them this way. I know it used to bother me. I used to get really upset because usually you would get one number, right? Whenever you're doing these, your function would be like, oh, y equals 8x, plus 5 or something. And I could never tell the difference between the two. And in my mind, A and B were technically the same thing, but they're not. Okay? I want you to think about B as the starting point. As a starting point. So if x was 0, then this is what I have in my hand. So if you're thinking about like, usually it's like nuclear waste, right? Well, I've got like these 10 tons of nuclear waste I bought on Amazon. I got it in 2 days with prime shipping. So at time 0, that's how much I would have, correct? That's what B represents, is what you start with. And then what A is going to do, it's going to be that rate of decay. So it might be half, so I'm getting half of the amount every single time. Or maybe if it's exponential growth, then that's what I'm growing by every single time. So 2 different things. B is what I would start with, and A is my I don't want to say delta y, delta x. It's my change. Okay? So 2 very different numbers. And they'll ask you questions about those. What does A represent here? What does B represent? So the way I think about B is kind of like a y-intercept, if you will, in this scenario. If time is 0, what do I have in my hand? Okay? Rate change. Starting, it looks like shortening or something like that. B is my starting point. Here. Start amount. Think about it that way. It's the start amount.
No, don't change.
what do you call a cow with no legs? That's so funny.
No, wait, what do you call a cow with 3 legs?
What do you call a fish with no eyes?
Lean meat. You got 3 legs, lean meat. We need a cow. What do you call a cow with 2 legs? What do you call a cow with
All right, we're good. Waterfalls. I didn't pull the joke at all. All right, any question on this slide? Can I move it? I can move on?
I have a question.
Yes.
So the H and the K, they only have to do with when you're moving it?
Yeah.
Would that be the vertex or no way?
No. Now, thank you for asking that. Usually, we always used to follow the point 0, 0, right, when we're working with parabolas. When we were working with cube functions, it was even still 0, 0, right? Because it was right in the middle. But remember how you just could change around. That's why we always pick 0, 0. I know. When we're working with these aren't parabolas. When we're working with exponential growth models, we're not going to track the point 0, 0 anymore. We're actually going to track the point 0, 1.
Always?
Yes. You always want to track that point.
0,
Yeah, 0, 1. Now, of course, that's the one that's going to be moved around. So, what does that do for your, I want to say vertex, but I would call it the starting point. That's kind of what I've been calling it, and that's how I think about it in my mind. That's my starting point, okay? That it won't be necessarily at h comma k like it usually was. It would be at h comma k plus 1.
Wait, H comma K plus 1?
Right. Is that right? H is side to side, K is up, yeah. Cool beans?
It do be big.
Good. I can change the slide now? There's no questions here? None? All right, cool. Evaluating exponential functions. Thank you. Waterfalls. So as you take a look at this, okay, the exponential function f of x is equal to 42.2 times 1.56 to the x models the average amount spent. F of x is in dollars. At shopping mall after X number of hours, what's the average amount of time that we spent? So this is a good example to take a look at. A and B aren't necessarily the same number, okay? So if I go and I'm spending money, what is it in, what kind of money?
Dollars.
That's a little bit of money.
Yes. Monies. 5 monies.
Well, this is pretty obvious, right? Like, all you really have to do with this is plug 3 in for X X amount of time. But if you think about this, this is how much I would be spending originally. So if I spent no time there, I already paid, no, because that would be 0. That would be 1. I would be paying 42.2 as soon as I got there. I don't know, maybe it's the valet parking. Something. But imagine that's what you're starting with, and then that's what your growth rate is. All right, cool beans. So here's that problem. No, it's a different problem. So here's just simply 3 to the x. Here's what it looks like. Notice it still crosses through 0, 1. And that should make sense because whenever x is 1 as an exponent, what happens to the entire part of it? You just get 1, right? Anything to the 0 power is 1. And this is why we always track the point 0, 1 and not 0, 0 anymore. Okay? Cool beans. Do I really need to say anything about this? Just plug and chug. Negatives ends up flipping it. Okay. I did want to point something out. Maybe I'll get to it later. I don't want to jump the gun here. Could we do something like this? This is old primitive input output. Isaac.
Yeah.
Welcome back. I'm just saying, can we do this? Input outputs. Sketch a graph based on that.
Yeah.
All right, cool beans. Moving on. So here's some stuff that you need to know. Oh my goodness. I should have chunked this down. All right. This reminded me of Bubble Bobble.
What?
There was a There was a Nintendo game called Bubble Bobble.
You have to turn it off and turn it back on. My computer does
I
it.
dismissed it.
No, the sound.
Oh yeah.
The sound.
Yeah, the game was called Bubble Bobble. It's an amazing game. I loved it. It was on the old NES. So let's go through this real quick. Number one. Thank you. Number one. The domain of this function consists of all real numbers. That should make sense. X is going to be growing. Sorry. X is going to be growing forever. This is a positive one. Just give FYI. X is going forever, but it would also technically be decreasing forever. If this was kind of decaying in the other direction, and if you think about taking half of something, right? If I had a piece of paper, I took half of it, I'd have half. Then half of that would be a quarter. Half of that would be an eighth. Then I would go 16th, a 32nd, 64th, and so forth, so forth, so forth. Technically, how long could I cut this piece of paper for? And that's what we have going on this side. So it's infinitesimally small.
There's a C right over there for you.
The graphs of these exponential growth models will always cross through the point 0, 1. And I think I talked about it, why already. No matter what you put in, anything to a 0 power will always be Guantanamera. The blue model, that is exponential growth. The red model is exponential decay. I want to point out this what the B values are. Remember I said that for growth, B has to be bigger than 1? If you want it to be decay, it has to be some number between 0 and 1. So I'm saying it's got to be a fraction because you're always taking a little chunk of it, right? Anytime you have a decimal in there, you're just taking a piece of something. So I want to point this out in a different slide real quick here. So y equals, let's go a, b to the x. B has to be less than 1, but greater than 0. Now it cannot be 0 or 1. Both of those are going to take you back to just a linear model. But you want some type of decimal to be up front. That's going to give you exponential decay. There's another way to get exponential decay. The other way is to make x a negative number. Because if you make x a negative number, then what do you have? Can you have a negative exponent? You cannot, right? So what do you have to do to make it positive? Is to flip the base. And by flipping the base, you're going to introduce some decimal fraction up in the front. So both of those are very legit ways of getting exponential decay. So if this is negative, or if your A or B value, sorry, is some number between 0 and 1. Okay? Why am I putting A there? I'm going to go ahead and stop there just because there's 2 minutes. Do that exit ticket, please. See if there's any questions. And then we'll pick it up, Manana, from here.
But he didn't like he was born in Red Rock. Yeah, so he suddenly just asked me. I know.
Y'all throw chamoy on the hot Cheetos, ¿verdad?
Thank you.